Pauli Effect. You are in a quiet lab. A meter hums, and the readout freezes the moment one person walks through the door. It sounds like superstition. It also sounds like every lab anecdote you have ever heard. Wolfgang Pauli was one of the giants of physics, but colleagues told stories. In one lab, an expensive instrument stopped working the same day his train passed through town. At Princeton, the cyclotron caught fire and burned for 6 hours during his visit. At a reception, a prank was set to drop a chandelier when he entered. But the mechanism jammed and the lamp stayed up, which only gave the story more life. Here is what is really happening. These are mostly human stories about coincidence and attention. Machines fail all the time. People remember the odd coincidences where a crash and a famous person align. That is confirmation bias. People notice patterns that support a colorful tale and forget the steady stream of normal days when nothing strange happens. Still, the Pauli effect matters because it exposes how scientists handle surprise. They laughed about it, they told stories, and they used the tales to warn each other about fragile setups. Labs began logging conditions, isolating equipment, and treating human factors like part of the experiment. That is a real change born from folklore. So, was the effect supernatural? No. Did the stories teach better lab practice? Yes. The lesson is simple. If physics stops working on paper, the first place to look is the human and the machine, not immediate rebellion of nature. But sometimes, the odd stories that start as jokes point to deeper problems, and we will see cases like that later. What changed after the stories spread was not magic. Labs became more careful. Researchers began writing down who touched what and when. They added redundancy. They moved fragile gear to isolated rooms and ran experiments remotely when possible. Those are small fixes. They are also the kind of fixes that stop a joke from becoming a catastrophe. There is a second lesson. Folklore like this forces scientists to look at the messy parts of practice. It leads to better logs, better maintenance, and better experimental design. That is real progress prompted by a funny superstition. It also shows how easily human attention shapes what we call data. When something strange happens, you notice it. When nothing happens, you usually forget it. That selective memory creates stories that feel meaningful even when they are not. Still, there is a harder truth. Not every breakdown is explained by a loose cable or an unlucky coincidence. Sometimes instruments show behavior that cannot be swept away by better housekeeping. Sometimes data refuses to fit the theory and keeps coming back even after controls improve. Those are the moments that make physicists uneasy because they point to limits in understanding. So when a lab says physics stopped working, your first move should be skepticism and method. Check the human. Check the machine. Check the math. If the anomaly survives those checks, then you are looking at something that could reshape knowledge. That is where the story stops being a joke and starts becoming serious. Cold fusion controversy. It began with a quiet lab announcement that sounded like a solution to the world's energy problem. Two chemists at the university announced they had produced fusion at room temperature. They said their setup was simple. They said excess heat appeared without the extreme temperatures everyone thought were needed. For a day, it felt like a miracle. Papers and headlines moved faster than the experiments. Here is the problem. Fusion, as scientists understand it, leaves clear nuclear fingerprints. You get neutrons and specific isotopes. Those markers were missing or inconsistent. Teams rushed to reproduce the work and could not. The American Physical Society held a special session in the spring of 1989, where many groups reported failure to replicate the heat or the nuclear signals. That failure does not always mean a claim is false, but it does mean the claim did not survive the essential test. Replication is the backbone of reliability. When independent labs cannot repeat the effect, something is wrong. Sometimes it is poor controls. Sometimes it is wishful interpretation. Sometimes it is genuine experimental error. There is another twist. A small community kept studying what they call low-energy nuclear reactions. The U.S. Department of Energy reviewed the evidence and remained unconvinced. Yet decades later, the same agency offered targeted funding through Advanced Research Projects Agency Energy, providing $10 million to a handful of projects exploring similar phenomena. That move changed the conversation from ridicule to cautious curiosity. So, what happened between the headlines and the new funding? Were the original results a fluke, a mistake, or a hint of something we do not yet understand? The next part will examine the messy experiments, the controls that failed, and why a few scientists still pursue what others declared dead. Inside the lab, the experiments looked simple enough to be believable: a metal electrode soaked in heavy water, a meter that should read heat, a chemist watching the dial and hoping. The big flaw was measurement. Heat is tricky to measure. If you do not account for chemical reactions that produce heat without fusion, you can misread the meter. If the calibration is off, you think you have excess energy when you do not. Many early groups did not use blind controls. Some readings changed when the experimenter knew the expected result. That is a classic human problem. Then there was the missing fingerprint of fusion. Neutrons and tritium should appear if atomic nuclei are fusing. The counts were low or inconsistent. That mismatch is why so many labs failed to reproduce the effect. The story moved from an exciting claim to a lesson in experimental rigor. There was also the media pressure. The paper went public before thorough peer review. That rush changed incentives. Scientists felt forced to defend or debunk in headlines rather than in careful lab reports. Careers were affected. Trust was damaged. Decades later, a small community kept looking. They refined calorimetry. They tested different metals. They kept careful logs and blind protocols. That persistence mattered enough that the Department of Energy funded targeted projects and gave $10 million to explore low-energy nuclear reactions. That funding does not prove the original claim. It does mean the question is worth better experiments. So where does that leave us? Were Fleischmann and Ponce unlucky, sloppy, or onto something subtle that only careful modern methods can find? The answer will affect how we judge both scientific heroism and scientific haste. Schön Scandal. You sit in a packed seminar and watch slide after slide that looks like revolution. The audience leans forward. The data is too clean, the curves too perfect, and the claim is breathtaking. Jan Hendrik. Schön worked at a famous lab with fancy equipment and eager collaborators. He published a string of papers that suggested breakthroughs in organic semiconductors. His name rose fast. The problem came from a quiet observation. Other scientists noticed the same strange pattern repeating across different experiments. Tiny bumps in the noise, matched from one graph to the next. That should not happen. Noise is random. Copying the same noise is a red flag. When colleagues looked closer, they found duplicated figures and inconsistent metadata. An internal investigation followed. Investigators compared raw files and found the same graphs reused in different contexts. Numbers that should vary did not. Requests for original data met slow replies or evasions. The story moved from suspicion to formal inquiry. The conclusion was that many results were fabricated. The verdict removed dozens of papers and left questions about oversight that still echo. The fallout was public and personal. Young researchers who had built careers on those papers scrambled to explain. Senior scientists who trusted a bright star felt betrayed. The lab that once sparkled with easy success had to rebuild trust. That repair work is part of the real story. Practical changes followed. Journals required authors to provide raw data and metadata. Peer review began to include data sleuthing in addition to theory checks. Co-authors were asked to verify their contributions. Labs instituted version control for experimental files and made replication reports part of performance reviews. Those are boring fixes, but they matter more than applause. There is a deeper cultural shift, too. Science became slightly less enchanted by single-star performers and more interested in slow, collective verification. That tempering of hero worship protects the field. This case is not just scandal, it is a lesson in verification. It shows that glamour and institutional prestige cannot replace careful checks. Still, unease remains. Fraud exposed a vulnerability. And the community learned the hard way that glamour can hide error. The next chapters will show different reasons physics can appear to stop working. Reasons that are not about lying, but about nature refusing to fit our best ideas. Who watches the data when the data seems most convincing? And how do we guard against being fooled by our own desire to believe? N-rays phenomenon. You are in a dim lecture hall in Paris. The room hushed, and a scientist claims to see a faint glow that no one else notices until they are told to look for it. The claim came from a respected researcher who said a new kind of radiation appeared under certain conditions. Other labs in the same country reported confirming sightings. The exposure felt like a small public unmasking. Scientists who had once nodded in agreement now felt uneasy when asked to replicate their results under blind conditions. The decisive tests were simple and elegant. An apparatus element would be moved without the observer's knowing. If the glow depended on the device, it should vanish. If it depended on expectation, the reports would continue. The results were plain. Reports tracked expectation, not apparatus. That clarity is rare and brutal. What followed was professional embarrassment and institutional soul-searching. Laboratories revised protocols. Conferences began to include stricter replication standards. Journals started demanding stronger controls before researchers claimed new radiation or new forces. Those changes were modest, but they tightened the net around future claims. There is a deeper lesson about human perception. Our senses are not impartial instruments. They are shaped by belief and context. When a respected voice in the community reports an effect, that voice changes what other people notice. That is how social proof can masquerade as physical proof, and how entire fields can drift toward consensus without hard tests. The N-rays story also shows how science corrects itself. A skeptic with a clever control did what the community had not. That single intervention saved years of wasted work. But it also left an uncomfortable memory. If honest observers can be swayed, how many other apparent effects were simply products of shared expectation? The question that lingers is sharp. When should we trust what many witnesses say, and when should we insist on experiments that remove the human observer entirely? Falsification of Element 118. You open a science bulletin, and the headline says a new element has been made, heavier than anything before, and suddenly the periodic table might get a new corner. Researchers at a major laboratory announced data that looked neat and conclusive. They reported decay chains and signals that would identify a super-heavy nucleus. The community leaned in because creating such an element is a rare and difficult feat that demands impeccable evidence. Skepticism arose when other teams could not reproduce the signals. Colleagues asked for raw records and for independent checks. Investigators found inconsistencies in the data files and problems that suggested fabrication rather than honest error. The claim was retracted, and reputations suffered. Why is this case so damaging? Synthesizing super-heavy elements relies on tiny signals buried in noise. Experiments are costly and rare. A false claim wastes time, diverts resources, and can mislead the direction of an entire subfield. It also bruises public trust in big science. There is a second act. Years later, other teams, using different machines and methods, produced consistent evidence for element 118. That work stood up to independent verification, and the element entered the record under a new name. The correction shows science can recover, but the episode left scars. The lesson is stark. When the prize is big and the signal is small, Extraordinary caution is required. One lab announcing a revolution is not enough. Verification, open data, and independent reproduction are the guardrails that keep the periodic table honest. How do we make those guardrails stronger for the next claimed miracle? The investigation began not with a headline, but with a spreadsheet. Colleagues compared raw files and noticed mismatches in timestamps and in detector logs that should not vary. Those details are easy to overlook and deadly when missed. Independent reviewers requested original recordings and beam logs. When those files arrived, they did not align with published figures. Signals were claimed at times when the beam was off. Metadata told a story that the polished paper did not. The lab retracted the claim, and the community felt embarrassed and betrayed. Consequences followed. Funding bodies tightened oversight for rare and expensive experiments. Collaborations now require independent verification steps before grand announcements. Data provenance became a formal part of proposals. Those changes add friction, but they also protect the integrity of discovery. The sting of the episode was real. Young scientists who had cited the work had to revise projects. Trust between labs frayed for a time, yet science has a way of fixing its record. Other teams used different accelerators and detector arrays, and after careful, repeated trials, they observed consistent decay chains. The element was validated and accepted into the table under a new name that honored a pioneer in atomic research. That closing arc matters. It shows how false claims can misdirect effort and how rigorous replication can restore truth. It also shows an uncomfortable fact. Big claims need big checks. When a signal is tiny and the prize is huge, we must demand the hardest possible evidence. So, ask yourself, would you trust a single lab with a revolutionary claim, or do you want to see agreement from the whole field before we rewrite the textbooks? Sonofusion Claims. You hear a claim that sound can make nuclei fuse, that cavitation can squeeze atoms so hard they join together, and you tilt your head because fusion was supposed to need conditions like the sun. Russi Talyarkin and his team reported brief bursts of neutrons and tritium linked to collapsing bubbles in a liquid driven by sound. The effect, if true, would be astonishing and cheap compared with mainstream fusion efforts. That is why the announcement echoed through conferences and headlines. But there was a problem. Independent groups had trouble reproducing the specific neutron bursts. Some detector logs did not match expected background patterns. Questions multiplied about experimental controls and about whether external sources could have contaminated the measurements. That doubt led to formal inquiries. Investigations examined lab notes and data handling. Auditors compared detector logs from different days and found patterns that did not line up. That is a small detail until you realize small details are everything when signals are tiny. Review panels examined raw recordings, timestamps, and lab notebooks. They found gaps in the chain of custody for data and inconsistencies between reported neutron bursts and the background measurements. Some results appeared in published figures that the raw files did not support. Those are the kinds of mismatches that end careers. Review panels found instances where records did not align with published figures and where oversight was weak. Those findings resulted in strong criticism and in the retraction or undermining of key claims. The episode left careers and reputations scarred and left the field wary of similar dramatic announcements. Institutions responded. Funding reviews tightened. Journals added requirements for logging and for third-party verification of extraordinary detector claims. Laboratories put independent monitoring in place so that odd bursts would be recorded by systems that cannot be influenced by the primary team. Those are practical steps born from hard lessons. The scientific community reached a somber conclusion. The specific claims did not hold up to independent replication. That is not the same as saying the whole idea is impossible. Sonoluminescence remains real and intriguing. The physics of collapsing bubbles still attracts careful labs who study light emission, heating, and extreme microphysics. Researchers continue to explore the phenomenon without claiming cheap fusion. There is a more subtle takeaway. Sonoluminescence, the bright flash produced by a collapsing bubble, is real and scientifically interesting. That fact gave the Sonofusion claim plausibility. But plausibility is not proof. When a result challenges deep expectations, we need replication under blind protocols and independent detection systems. The social cost was high, trust was damaged, and a field learned to be wary of dazzling announcements. Young researchers adjusted how they publish and how they share raw files. The culture shifted toward transparency and reproducibility. There is a final, sharp lesson. When a claim asks us to accept a miracle with small evidence, demand the hard records, the blind checks, and the independent detectors that cannot be waved away. If that threshold is not met, the claim should not change our textbooks or our funding priorities. So where does that leave us? Was there an honest mistake amplified by ambition and sloppy controls, or was there misconduct? The investigations leaned one way. The science community learned to treat dazzling claims with the kind of skepticism they demand for themselves. When does caution become obstruction, and when does trust become gullibility? Room temperature, superconductivity, claims. You open a paper that promises a world where power moves without loss at ordinary temperatures, and you feel a sudden jolt of hope. The claim was simple and seductive. A material, treated one way, showed zero resistance near room temperature. The implications are obvious. Power lines without loss, faster electronics, a huge leap for technology. The paper gathered attention because the data looked clear, and because the experimental setup sounded achievable. Then doubts crept in. Other groups could not reproduce the results. Careful readers noticed duplicated plots and suspicious image edits. Metadata did not line up with the published figures. Journals and institutions launched inquiries. Reviewers asked for raw data and for full experimental logs. In several cases, the metadata did not match the published figures. Image edits and duplicated plots undermined confidence. An investigation followed and found evidence that some data had been manipulated. The core result was withdrawn, and the papers were retracted in 2020. The fallout was serious. Promising careers hit obstacles. Funding agencies became more cautious about early hype. Journals updated policies requiring raw data availability and clearer descriptions of methods. Labs tightened their internal checks, and many teams began to publish pre-registration of experiments, so others could see plans before results appeared. That outcome did not kill the field. It changed it. Superconductivity research is now more cautious and more rigorous. Yet the field did not collapse. Researchers studying superconductivity at extreme pressures continued to push forward. Those experiments are technically difficult and demand independent verification. Some high-pressure results have been reproduced and are promising. They do not, however, deliver lossless conduction at ambient pressure and ambient magnetic fields. Groups studying hydrogen-rich compounds at extreme pressures continue to report impressive results, but those require independent verification and full data sharing before the community will accept them. The episode left two enduring lessons. 1. Extraordinary promises demand extraordinary documentation. 2. The path to real breakthroughs is often slow and incremental. Headlines love revelation. Scientists prefer reproducible facts. The episode taught two lessons. First, the bigger the prize, the higher the burden of proof. Extraordinary claims demand extraordinary records. Second, legitimate progress can be messy and incremental, and it is easy to mistake plausibility for proof. When headlines shout a revolution, scientists ask for raw logs, blind replications, and independent detectors. So where do you place your trust? In a single dazzling paper that promises to change everything, or in careful teams that publish raw logs and invite others to replicate? The right balance decides how fast a field moves and how often it stumbles into headlines that later need correction. So ask yourself, Do you want to celebrate early findings that sound miraculous, or do you want the slow, careful confirmation that turns miracles into reliable technology? Michelson-Morley Experiment. You set up mirrors and a beam of light. You split that beam and send each half down a different arm, and you expect a tiny shift when the arms are recombined because the Earth moves through the ether. Albert A. Michelson and Edward W. Morley did that experiment in 1887 with exquisite care. They used an interferometer that could detect differences smaller than the width of a human hair. The expectation was simple. If an ether carried light, the motion of Earth would change the travel time along one arm relative to the other. The instrument should show a shift. It did not. That null result was not sloppy data. It was repeated with improved equipment and at different times of year. The effect remained absent. The obvious conclusion was that the presumed ether either did not exist or behaved in a way no one had imagined. That put theorists in a corner. Scientists reacted in stages. Some tried ad hoc fixes. Others proposed more complex ether models. Years later, a young patent clerk proposed a simpler view. Albert Einstein suggested that the speed of light is constant for all observers, and that space and time have to adjust. The null result of Michelson and Morley was one of the pieces that made that leap possible. This is a different flavor of breakdown. It is not human error or misconduct. It is a case where nature refused to fit an assumption. The payoff was profound. Physics did not collapse, it evolved. The experiment shows how a careful null result can be more dangerous to established ideas than a dramatic anomaly. So, how sure should we be when our most faithful instruments report nothing at all? The null result forced a rethink. The simplest answer was uncomfortable. If the ether did not show up in the lab, then the idea that light needed a medium was wrong. Physicists worked through the implications. Some tried to fix the ether idea with clever adjustments. Others looked for a deeper change. A few years later, a young physicist proposed a different starting point. He suggested that the speed of light is the same for all observers, and that measurements of space and time must adjust. That sounded radical, but it explained the stubborn null of the interferometer. The result was special relativity. It rewrote basic concepts of simultaneity, of time, and of length. That theoretical leap was not just elegant thinking, it made testable predictions. Later experiments confirmed time dilation and mass energy equivalence. The new framework allowed physicists to build technologies that rely on precise timing. Modern navigation systems correct clocks using relativistic formulas because the differences add up if ignored. That is a practical echo of a careful null result in a lab a century earlier. The Michelson-Morley story is a reminder that a careful zero can be more powerful than a noisy anomaly. It shows science at its best when instruments are trusted, when repeated nulls are taken seriously, and when theorists are willing to change the foundations. If a measured nothing can change everything, how should we treat the nulls and the anomalies we see today? Checking solar neutrino problem. The second section starts with, deep under the ground, a detector counted ghost particles, and the total did not match the sun models, but a different detector told a different story. Assessment. This opening is okay, but could be smoother. E. Issues. Deep under the ground, a detector counted. This somewhat repeats the first sections. An experiment deep in a mine started counting them, but a different detector told a different story. This is new information, the breakthrough, but feels abrupt without transition. However, it's not as problematic as the others because it doesn't say the first time or create an obvious loop. It advances the story to the solution phase. The repetition is minimal. Solution. Remove or modify the opening sentence. Start with, the breakthrough came when instruments could see neutrino types, not just counts. Or, keep a brief setup but make it smoother. The breakthrough came when a different detector told a different story. Let me give you the complete merged version. Complete merged explanation for solar neutrino problem. Solar neutrino problem. You point a detector toward the sun, expecting a steady trickle of ghost-like particles, and you count far fewer than the models said you should. The sun makes energy by fusing hydrogen into helium. That process spits out neutrinos, tiny particles that barely interact with matter. In the 1960s, an experiment deep in a mine started counting them. The count came in low. That was a shock, because stellar models had worked well for light and heat. If neutrinos were missing, either the sun was wrong or the particle physics was wrong. For years, measurements and models argued. Different detectors reported deficits of similar size. The puzzle persisted for decades. Scientists checked the sun, the detectors, the calculations, and the backgrounds. They tightened the instruments, and the theory held up. That left a strange possibility. Maybe neutrinos were changing along the way. The breakthrough was to consider that neutrinos come in types, and that they can change types as they travel. That idea requires that neutrinos have mass. It was a small change in particle properties, with huge consequences. The breakthrough came when instruments could see neutrino types, not just counts. One observatory showed that the sun was sending the expected total number of neutrinos, but many had changed type on the way to Earth. That is called oscillation. It means neutrinos are shapeshifters that switch identities as they travel. Oscillation requires mass. That simple fact forced physicists to rewrite parts of the particle table. A particle once thought weightless now must have some mass, even if tiny. That change is small in everyday terms, but huge for theory because it opens new ways to think about how particles get mass and how the universe evolved. Experiments that could see all types confirmed the oscillation idea. The confirmation came from multiple experiments and from different detection methods. The result was robust enough to earn wide recognition and to reshape research priorities. The result won wide recognition and a Nobel Prize in 2015. The payoff is double. 1. The solar models were vindicated. 2. Particle physics needed revision. A particle once thought massless turned out to carry mass and to morph on the journey from the sun. The discovery also raised fresh puzzles. How much do neutrinos weigh exactly? Are they their own antiparticles? Could neutrinos explain why the universe has more matter than antimatter? Those are big questions that follow from a once puzzling deficit in a mine shaft counting quiet particles. That taught a lesson about humility. When data refuses to fit, sometimes the universe is nudging us toward new physics. The solar neutrino story is a model of science correcting itself. A stubborn mismatch led to careful measurements, to theoretical risk-taking, and to deeper insight. If tiny, almost invisible particles can force us to change basic physics, what other small effects might be hiding revolutions in plain sight? What other tiny effects are we still treating as noise that might hide a revolution? Pioneer Anomaly. You watch a probe that has left the major planets, and you expect your equations to tell you exactly where it should be. For Pioneer 10 and 11, the numbers did not match. Engineers tracking the spacecraft found a tiny extra acceleration, a steady tug toward the sun that the models did not predict. It was small, almost invisible, but it persisted as the probes sailed into deep space. That persistence is what made people listen. Scientists reacted in two ways. Some looked for new physics, ideas that would change gravity at long range. Others looked at the probes themselves. If your instrument is off by a hair, you can invent whole new forces by mistake. That split drove years of careful work. The puzzle became a forensic problem. Teams dug through telemetry, spacecraft plans, and thermal models. They asked how heat leaves a spacecraft and whether that escaping heat can push it. It turns out objects radiate photons, and photons carry momentum. If more heat leaves one side than the other, you get a tiny recoil. The idea is simple, and the math is precise. But the detective work is brutal. You must model heat generation, reflection, and shadowing across decades of telemetry. Early results were mixed, and controversy lingered. The possibility that gravity itself might need revision kept some researchers excited. The resolution arrived quietly, after years of patient work, not with a dramatic new theory. Researchers recovered decades-old telemetry and engineering drawings. They reconstructed how power from the radioisotope thermal generators and onboard electronics left the spacecraft. Heat leaves as photons, and photons carry momentum. If heat radiates unevenly, you get a tiny thrust. Teams built detailed thermal models that included the geometry of instruments, the reflectivity of surfaces, and changes over time. They compared simulated forces with the observed tiny acceleration toward the sun. The match was convincing. Most of the anomaly could be explained by anisotropic thermal radiation and by small reflections off structural components. That finding did something important. It closed a door on exotic modifications to gravity in this context. It also opened a different door. Engineers and scientists now appreciate that minute engineering details matter when you test fundamental physics in space. The probe was whispering about heat and design, not about a new law. There were broader consequences. The work showed the value of preserving raw telemetry and design archives. It showed how slow, careful modeling can beat flashy speculation. The pioneer story humbled some and taught others how to build better experiments to test gravity at large scales. The final lesson is practical and humane. When data and models disagree slightly, the answer is usually a patient audit of assumptions. Still, the episode is a reminder that even small residuals can tempt us toward grand ideas. So which way would the evidence bend? Would the anomaly force a rewrite of gravity, or would the probe tell a quieter story about heat and reflection? How much should a tiny mismatch change our theories? And how much should it change our curiosity and humility?